Hi everyone. Welcome to our channel. If you are here, you can just settle in. Find a comfortable position. Let your body relax into wherever you are resting right now. There is absolutely no rush. There is nothing you need to do, nothing you need to remember. You can simply listen, or let the words drift quietly past you, like a soft breeze through an open window. On a still night, tonight, we're going to travel together, very gently, to a time before there were stars, before there were planets, before there were you, or me, or anything we would recognize. We're going to talk about how galaxies are born, how these enormous, beautiful, slowly spinning collections of light came to exist in the darkness of space. And the wonderful thing is, there is no urgency in any of this. These are stories that unfolded over billions and billions of years. Slowly, quietly, without hurry. And so, we can take all the time we need to move through them together. You might fall asleep before we are done. That is perfectly fine. That is, in fact, a wonderful thing. The universe will still be here. The galaxies will still be slowly turning. And these soft, gentle ideas will be here whenever you would like to return to them. So, let us begin. Slowly, gently. There is no need to rush. Long before any galaxy existed, there was a time in the universe that scientists call the cosmic dark ages. And we can take a moment to notice just how peaceful that name sounds. The cosmic dark ages. It was a period that began roughly 380,000 years after the Big Bang, and lasted for hundreds of millions of years after that. During this time, the universe was filled almost entirely with a very faint, very thin gas, mostly hydrogen, and a little helium. There were no stars yet, no light, just this vast, dark, slowly cooling sea of gas, stretching in every direction, farther than we could ever imagine. And yet, even in that darkness, something was already beginning to happen. Very slowly, very gently, gravity was beginning to pull tiny wisps of gas, ever so slightly, toward one another. The universe was already, in its own quiet way, preparing for what was to come. The Big Bang itself, which is where we like to begin the story of everything, happened approximately 13.8 billion years ago. And we can take a quiet moment to feel the weight of that number, 13.8 billion years. If you counted one number every second without stopping, it would take you over 400 years just to count to 13.8 billion. That is how long ago the universe began. But the Big Bang was not really an explosion in the way we usually imagine explosions. It was not a loud bang in empty space. It was more like the universe itself began to expand. All of space, all of time, all of energy and matter simply started to grow, outward in every direction at once. And the early universe was extraordinarily hot and dense, almost unimaginably so. But slowly, gently, as it expanded, it began to cool. And as it cooled, the first simple atoms began to form, drifting quietly in the growing dark. After those first atoms formed, the universe entered that long, quiet period we mentioned, the cosmic dark ages. And it is worth sitting with this idea for a moment. For hundreds of millions of years, the universe was simply dark and quiet. There were no stars to light it, no planets, no life, just this immense, gently expanding sea of gas, and the invisible pull of gravity, working slowly, patiently, without any hurry. Scientists know about this period, not because they can see it directly. There was no light to see, but because of the subtle traces it left behind. The tiny variations in temperature and density that were already present in those early gases would eventually grow, very slowly, into the seeds of galaxies. It is a comforting thought, in a way, that even in the deepest darkness, something is already quietly and gently becoming. One of the most beautiful ideas in all of cosmology is something called the cosmic microwave background. and gently moving forward. Let us think about what that is. When the universe was still very young and very hot, it was filled with a kind of glowing light, a warm, bright haze that permeated everything. As the universe expanded and cooled, that light could not travel freely at first. The universe was too dense, like a thick fog. But about 380,000 years after the Big Bang, the universe cooled enough that the fog cleared, and that ancient light was finally free to travel. It has been traveling ever since, for over 13 billion years, and today it reaches us as a faint, soft glow of microwave radiation that fills the entire sky. Astronomers can detect it with special instruments. It is the oldest light in the universe, a gentle, lingering whisper from the very beginning of time, within the cosmic microwave background. Scientists have found something extraordinary. Very tiny, very subtle differences in temperature. Some regions of that ancient glow are just barely, almost imperceptibly, warmer than others. We're talking about differences of about 1 part in 100,000. Incredibly small. And yet, those tiny differences were the seeds of everything. They represented the very first unevenness in the distribution of matter across the universe. Where the gas was ever so slightly denser, gravity would eventually pull more gas toward those spots. And those spots, over hundreds of millions of years, would slowly become the first galaxies. So in a very real sense, every galaxy you have ever seen, in a photograph of deep space, every spiral, every cluster, every soft smear of light, began as the faintest imaginable whisper of difference in the temperature of the very young universe. Slowly, gently, those differences grew into everything. Gravity is the force that built the universe as we know it, and there is something very calming about the way gravity works. It does not rush. It does not push. It simply pulls, very gently, very persistently, over immense stretches of time. In the early universe, where the gas was slightly denser, gravity would pull in just a little bit more material, and that extra material made gravity slightly stronger, which pulled in just a little more material. It is a slow, patient process. Scientists call it gravitational collapse, and it unfolded over tens of millions, even hundreds of millions of years. There was no dramatic moment, no sudden event, just a quiet, steady gathering of matter, slowly accumulating in the dark. And we can take a moment to notice that this is how many of the most beautiful things in the universe are made. Not quickly, not dramatically, but slowly, gently over time. The very first structures to form in the universe were not galaxies. They were smaller, much smaller, collections of gas and dark matter that scientists call mini-halos. And let us take a quiet moment to think about dark matter, because it played a very important role in all of this. Dark matter is a mysterious substance that we cannot see directly. It does not emit light. It does not reflect light. We know it exists because of the way it affects the things around it through gravity. And in the early universe, dark matter gathered into these small, invisible halos first. The ordinary gas, the hydrogen and helium, then slowly fell into those dark matter halos. Drawn in by gravity, those halos acted like invisible scaffolding, or like the gentle framework of a spider's web, holding the structure together, while the visible matter slowly gathered within. It is a quiet partnership, ordinary matter and dark matter, building galaxies together across deep time. The first stars in the universe are believed to have formed somewhere around 100 to 200 million years after the Big Bang. And these were not stars like our sun. They were likely much, much larger. Scientists call them population 3 stars. And they were made almost entirely of hydrogen and helium, because those were the only elements that existed at the time. Everything else, the carbon, the oxygen, the iron, the gold, had not been created yet. These enormous ancient stars burned very brightly, And very briefly, because of their great size, they burn through their fuel quickly, lasting perhaps only a few million years, before exploding as supernovae. And those explosions were important, because they scattered the first heavier elements out into the surrounding gas, gently moving forward. Those elements would eventually be incorporated into new stars and new worlds. Everything is connected across time. Slowly and quietly, when those first massive stars exploded, they released something very important into the universe. The heavier elements that would later be needed to build rocky planets, and eventually life. Before those first stellar explosions, the universe contained almost no elements heavier than lithium, carbon, nitrogen, oxygen, silicon, iron. All of these were forged inside the hearts of those early stars through a process called nuclear fusion. And when the stars died, they scattered those elements outward. Scientists have a lovely, poetic way of describing this. They sometimes say that we are all made of stardust. Every atom of carbon in your body, every atom of oxygen in the air you breathe, every atom of iron in your blood was forged inside a star that lived and died long before our sun was born. We can take a quiet moment to rest with that idea. We are, in a very literal sense, made of ancient stars. The process by which matter clumped together under gravity to form the first galaxies is called hierarchical structure formation. It is a long phrase, but the idea behind it is actually quite gentle and simple. It means that the universe built big things out of small things. First, tiny clumps of gas and dark matter formed. Then those small clumps slowly merged with other small clumps. Over time, those merged clumps became larger, and those larger ones merged again. And slowly, very slowly, over hundreds of millions of years, small structures grew into larger ones. This is how the very first proto-galaxies formed. Not all at once, not in a single dramatic event, but through a patient, ongoing process of accumulation. Small things coming together, medium things coming together. Eventually, the recognizable shapes of galaxies emerging from the dark, like a soft light slowly brightening on the horizon. The first true galaxies are believed to have formed somewhere between 200 million and 500 million years after the Big Bang. They were not like the grand spiral galaxies we see in photographs today. They were small, irregular, and somewhat chaotic in shape, but they were galaxies, collections of stars, gas, and dark matter, held together by gravity, slowly turning in the dark. Scientists have recently been able to glimpse some of these earliest galaxies, thanks to powerful space telescopes. And it is a remarkable thing to look at an image of a galaxy and realize that the light you are seeing left that galaxy over 13 billion years ago. That light has been traveling through space for almost as long as the universe has existed, and now it has arrived, gently, to be recorded by a telescope floating quietly in space. The universe has a slow, patient kind of beauty. The James Webb Space Telescope, which was launched in 2021 and began its observations in 2022, has allowed astronomers to see farther back in time than ever before. And some of its early discoveries gently surprised scientists. It found galaxies that appeared to be larger and more developed than many models had predicted for that early period in the universe's history. This is one of the wonderful things about science. We build careful, thoughtful models of how we think things work, and then the universe shows us something slightly unexpected, and we take a quiet moment to reconsider, not with alarm, but with curiosity. The universe is under no obligation to match our models exactly. It is simply doing what it does, slowly and patiently, across billions of years, and we are lucky enough to be here, at this particular moment, with instruments sensitive enough to begin to see it. One of the most important ideas in understanding how galaxies formed is the concept of a protogalaxy. A protogalaxy is, in a sense, a galaxy in the process of becoming. It is a large cloud of gas and dark matter that has begun to collapse under gravity and has begun forming its first stars, but has not yet fully settled into the organized shape we might recognize as a mature galaxy. Protogalaxies were very common in the early universe. They were irregular, turbulent in a slow kind of way, and actively forming new stars at a very high rate. Over time, through a combination of gravitational settling, merging with other protogalaxies, and the gradual depletion of raw star-forming gas, these early structures slowly evolved into the galaxies we see today. It is a long, patient transformation, like watching a cloud slowly resolve itself, over billions of years, into a clear sky. Dark matter, which we touched on earlier, makes up approximately 27% of the total content of the universe. Ordinary matter, the kind that makes up stars, planets, gas clouds, and everything we can see, makes up only about 5%. The rest, roughly 68%, is something called dark energy, which is even more mysterious, and which we will return to gently later on. But for now, let us sit with this quiet fact, that everything we can see, every star and galaxy and nebula, in all the photographs ever taken, represents only about 5% of what the universe contains. The vast majority of the universe is invisible to us, and yet, in a very real way, that invisible material, particularly dark matter, is what shaped the universe we see. It provided the gravitational framework, the silent, invisible scaffolding, upon which the visible universe was slowly, gently built. When we look at images of the large-scale structure of the universe, images that map the positions of millions of galaxies across vast stretches of space, we see something that scientists call the cosmic web, and it is one of the most beautiful structures in all of science. Galaxies are not scattered randomly through the universe. They are arranged along long, thin filaments of matter, like beads on a string, or like the threads of a very large and very delicate web. Between those filaments are enormous empty regions called cosmic voids. The overall structure looks remarkably like the structure of a neuron in the human brain, or like a sponge, or like frost forming on a window. All of these enormous filaments and voids trace the original distribution of dark matter in the early universe. The universe, in its very structure, carries the memory of its own earliest moments. Galaxies come in a wonderful variety of shapes and sizes, and gently moving forward, let us take some time to think about the most common kinds. The first, and perhaps the most familiar, is the spiral galaxy. Spiral galaxies have a bright central region, called the bulge, surrounded by a flat, rotating disk, with long curving arms that spiral outward from the center. Our own galaxy, the Milky Way, is a spiral galaxy, so is the Andromeda galaxy, our nearest large galactic neighbor. The spiral arms are not actually fixed structures. They are more like slow waves, passing through the disk, regions of slightly higher density, where new stars are more likely to form. So when you look at a spiral arm, you are not seeing the same stars you would have seen a billion years ago. You're seeing a slowly moving pattern, like a ripple, slowly crossing a still pond. Elliptical galaxies are another common type, and they have a very different, very calm character. They are roughly oval or spherical in shape, smooth and featureless. They contain mostly older, reddish stars, and very little gas or dust compared to spiral galaxies. This means they are not forming many new stars. They have in a sense settled. They have used up or expelled much of their star-forming material, and now they glow with the quiet light of older stars. Some elliptical galaxies are among the largest galaxies known. Giant elliptical galaxies can contain trillions of stars and span hundreds of thousands of light years. They often sit at the center of large galaxy clusters and are thought to have grown to their enormous sizes through repeated mergers with other galaxies over billions of years, slowly accumulating, slowly growing, like a quiet pool of light in the dark. Then there are lenticular galaxies, which are a kind of gentle middle ground between spirals and ellipticals. They have the disk shape of a spiral galaxy, but they lack the prominent spiral arms. They also tend to have less star-forming gas than spirals. Scientists think lenticular galaxies may be spiral galaxies that have slowly lost their gas over time, perhaps stripped away by interactions with other galaxies, or simply used up, and so they sit quietly in between, retaining the flat disk of their spiral past, but slowly fading into something calmer, more settled. There is something peaceful about that, a galaxy slowly transitioning from active star formation to a quieter, more contemplative state. Still beautiful, still turning, just more quietly than before. Irregular galaxies do not fit neatly into any of the other categories. They have no clear spiral arms, no smooth oval shape. They are, as the name suggests, irregular, somewhat chaotic in appearance. Many irregular galaxies are thought to be the result of close encounters or collisions with other galaxies, which distort their shapes and trigger bursts of star formation. The Large Magellanic Cloud and the Small Magellanic Cloud, which are two small galaxies that orbit our own Milky Way, are good examples of irregular galaxies. They are visible to the naked eye from the southern hemisphere, looking like detached pieces of the Milky Way. They are neighbors of ours in the cosmic sense, relatively close, gravitationally connected, slowly being drawn toward us across deep time. We can take a quiet moment to notice how gently even galactic relationships unfold. Our own galaxy, the Milky Way, is classified as a barred spiral galaxy. That means it has a central bar-shaped structure, made of stars, from which the spiral arms extend. From a great distance, if we could somehow see it from outside, it would look like a glowing pinwheel, with a bright bar across its center. The Milky Way is roughly 100,000 light-years across. That means light, traveling at 300,000 kilometers per second, the fastest anything can travel in the universe, would take 100,000 years to cross from one side to the other. It contains somewhere between 200 billion and 400 billion stars. Our Sun is just one of those stars, located about halfway out, along one of the spiral arms. We live in a very ordinary part of a very large and quietly beautiful galaxy. Inside galaxies, new stars are born in clouds of gas and dust, called nebulae, and there is something very calming about the way this process works. A nebula is a vast, diffuse cloud, sometimes spanning hundreds of light years, made mostly of hydrogen gas, with traces of helium and dust. These clouds drift gently through the galaxy. Most of the time, the pressure of the gas pushing outward balances the gravity pulling inward, and the cloud remains stable, just drifting quietly. But sometimes, something disturbs the cloud. Perhaps the shockwave from a nearby supernova, perhaps a gentle collision with another gas cloud, and that disturbance can cause part of the cloud to begin to collapse under its own gravity, very slowly, very gently at first, and that collapse, over millions of years, will eventually give birth to new stars. Life and stars begin in slow, quiet collapses. As a region of a nebula collapses under gravity, it begins to spin. This is a consequence of something called the conservation of angular momentum. Think of it this way. If you have ever watched a figure skater pull their arms inward to spin faster, you have seen this principle at work. As the gas cloud collapses inward, it spins faster and faster. The collapsing gas forms a rotating disk. And at the center of that disk, material continues to fall inward and compress and heat up. Over time, the core of the collapsing cloud becomes hotter and denser, until eventually, the temperature at its center reaches about 10 million degrees. And at that point, nuclear fusion begins. Hydrogen atoms begin fusing together to form helium, releasing enormous amounts of energy, and a new star is born, slowly, gently, out of a collapsing cloud of gas that has been drifting quietly through space. The disk of gas and dust that forms around a young star is called a protoplanetary disk, and it is a beautiful thing to think about. This flat, rotating disk of material surrounds the young star like a very thin, very wide ring. Within that disk, tiny solid particles of dust gently collide and stick together. Over time, those dust grains grow into pebbles. Those pebbles grow into rocks. Those rocks slowly accumulate into larger and larger bodies, called planetesimals, and eventually into the rocky cores of planets. This entire process, from a collapsing cloud of gas to a fully formed planetary system, can take anywhere from a few million to tens of millions of years. And through all of that time, gravity is the quiet, patient force doing the work, slowly gathering, slowly shaping, slowly building worlds. Out of dust and time, the rate at which a galaxy forms new stars is called its star formation rate, and this rate has changed dramatically over the history of the universe. In the early universe, when galaxies were young and full of fresh gas, star formation rates were very high. Galaxies were churning out new stars at a remarkable pace, but over billions of years, as galaxies used up their star-forming gas, those rates slowed. The universe reached what astronomers call the cosmic noon, the period of peak star formation, roughly 10 billion years ago. Since then, the overall rate of star formation across the universe has been slowly declining. Our own Milky Way currently forms about 2 or 3 new stars per year, a quiet, steady pace. The universe is not in a hurry. It never has been. It is simply continuing, slowly and gently, as it always has. Some galaxies undergo sudden, dramatic bursts of star formation, and these are called starburst galaxies. These events are often triggered by gravitational interactions or mergers with other galaxies. When two galaxies pass close to each other, or even collide, the gravitational disturbances can compress large amounts of gas very quickly, triggering the formation of many new stars in a relatively short period of time. Starburst galaxies can form stars at rates hundreds or even thousands of times higher than a quiet galaxy like the Milky Way. But these bursts do not last forever. The intense radiation and stellar winds from the newly formed stars eventually blow away or heat up the remaining gas, shutting off further star formation. A burst of creativity, followed by a long, quiet settling. There is something very familiar about that rhythm. At the center of most large galaxies, there is a supermassive black hole. Our own Milky Way has one at its center. It is called Sagittarius A*, and it has a mass of about 4 million times the mass of our Sun. And yet, it is relatively quiet. It is not currently consuming much material, and so it does not produce much energy. Many galactic centers are far more active. When a supermassive black hole is actively consuming gas and other material, it can produce enormous amounts of energy, and the galaxy is said to have an active galactic nucleus, or AGN. The most luminous of these are called quasars, and we can take a quiet moment to notice something remarkable. Even the most powerful, most energetic objects in the universe, these blazing quasars, are at their heart simply gravity doing its patient work, drawing matter inward. Slowly, inevitably, supermassive black holes are thought to play an important role. in regulating star formation in galaxies. When a black hole at the center of a galaxy is actively consuming material, it releases tremendous amounts of energy in the form of radiation and powerful jets of particles. This energy can heat up and push away the gas in the surrounding galaxy, making it harder for that gas to cool down and collapse into new stars. So in a strange way, the very thing that might seem like a force of pure consumption, a black hole devouring material at the center of a galaxy, is actually helping to regulate the birth of new stars. It is a quiet kind of balance, an interplay between formation and suppression, between the inward pull of gravity and the outward push of energy. Gently, the universe maintains its own equilibrium. Across cosmic time, the supermassive black hole at the center of our Milky Way, Sagittarius A*, was imaged for the first time in 2022 by the Event Horizon Telescope collaboration. This was only the second image ever taken of a black hole's shadow. The first, released in 2019, was of the black hole at the center of the galaxy M87, which is far larger, about 6.5 billion times the mass of our Sun. Both images show the same quiet, circular shape, a dark region, surrounded by a soft, glowing ring of light. That ring is the light of gas and dust that has been heated to extreme temperatures. As it spirals inward, the dark center is the shadow of the black hole itself, the region from which no light can escape. It is in its own way a very calm image, a circle of darkness, surrounded by a ring of soft light. The universe, showing us its own quiet depths. Scientists believe that supermassive black holes and their host galaxies grow together over time. This coevolution, as it is called, is one of the more fascinating puzzles in modern astronomy. The mass of a galaxy's central black hole tends to be closely related to the mass of the galaxy's central bulge of stars. This suggests that somehow, the growth of the black hole and the growth of the surrounding galaxy are linked, that they influence each other, that they're, in some sense, growing up together. The exact mechanisms of this relationship are still being studied, but the broad picture is one of a long, slow, gentle coexistence. A black hole and a galaxy, each quietly shaping the other's development. Across billions of years, there is a certain tenderness in that image. Two immense things, slowly, quietly, becoming what they are together. Let us take a quiet moment to think about something called feedback. In the context of galaxy formation, feedback refers to the ways that the energy released by stars and black holes influences the gas and the environment around them. Stellar feedback includes the radiation, stellar winds, and supernova explosions from massive stars. These processes can heat and push away gas, disrupting star formation in some regions, while triggering it in others. AGN feedback, from active galactic nuclei, can do the same thing on a much larger scale. Feedback is a form of self-regulation. It keeps galaxies from converting all their gas into stars too quickly. It is one of the reasons the universe has the kind of structures it does today. Not a chaotic jumble of all the matter clumped into stars at once, but a slow, regulated, patient unfolding of structure across time. Galaxies are not isolated. They exist within larger structures, groups and clusters, and over time, they interact gravitationally with one another. When two galaxies pass close enough to each other, their mutual gravity can pull and distort them into remarkable shapes. Long tails of stars and gas can be drawn out between them. The shapes of both galaxies can be dramatically altered, and often, over hundreds of millions of years, the two galaxies will slowly spiral toward each other and eventually merge into a single larger galaxy. This process is called a galaxy merger, and it has been one of the key ways that large galaxies have grown over cosmic time. The universe builds large things out of smaller things, not just at the smallest scales, of gas clouds and stars, but at the grandest scales, of entire galaxies slowly spiraling toward each other. Across deep space, our own Milky Way is on a slow collision course with the Andromeda Galaxy. Andromeda is currently about 2.5 million light-years away from us, and it is moving toward us at roughly 110 kilometers per second in approximately 4 to 4.5 billion years. The two galaxies will begin to interact, and over the following billions of years, they will slowly merge into a new, larger elliptical galaxy. This event is sometimes called Milkomeda, a gentle combination of the two names. And while the word collision might sound alarming, it is worth noting that this will be an extraordinarily slow process. And because the space between stars is so vast, the actual stars within the two galaxies are very unlikely to physically collide with one another. The galaxies will pass through each other, distort each other, and slowly settle together. A long, slow, quiet dance across billions of years. When two galaxies are in the process of merging, they often trigger intense star formation. The gravitational disturbances compress large amounts of gas, creating the conditions needed for many new stars to form. This is one of the reasons that some of the most visually striking galaxies are merging pairs. The interaction between them lights them up with the blue light of freshly formed stars and the pink glow of star-forming nebulae. Scientists call these interacting systems things like the antennae galaxies or the mice galaxies, named for the long tails of stars that are drawn out by the gravitational interaction. They are beautiful, two enormous collections of stars, slowly moving through each other, their gravity gently reshaping both, their gas sparking into new starlight along the way. We can take a moment to notice how even destruction, at the scale of galaxies, creates something new and luminous. Not all galactic interactions involve full mergers. Sometimes galaxies simply pass near each other, exchanging gravitational influences, and perhaps sharing some gas or stars, before moving apart again. These flybys can still significantly alter the structure of both galaxies. A smaller galaxy passing near a larger one might have its shape completely distorted. The larger galaxy might acquire a ring structure or develop tidal tails. These interactions leave lasting marks on the shapes and star formation histories of galaxies. When astronomers look at the unusual shapes of many galaxies, the rings, the asymmetries, the long streamers of stars, they are often seeing the quiet evidence of close encounters that happened hundreds of millions of years ago. The past leaves its gentle imprint on the present. The universe carries its own history in its shapes. Galaxy groups and clusters are the largest gravitationally bound structures in the universe. Our own Milky Way belongs to a modest collection of galaxies, called the Local Group. The Local Group contains about 54 galaxies in total. The most of them are small dwarf galaxies. The Milky Way and Andromeda are the two largest members. The Local Group itself is part of a larger supercluster, called the Virgo supercluster, which in turn is part of an even larger structure, called Laniakea, a supercluster spanning roughly 520 million light-years, and containing the mass of about 100 million billion suns. And yet, even Laniakea is just one small region of the cosmic web. The universe contains an estimated 2 trillion galaxies. 2 trillion, and we can take a quiet moment to simply let that number rest softly in the mind without needing to fully comprehend it. Galaxies, like stars, have life cycles. They are born, they grow, they evolve, and eventually they reach a kind of old age, a quiet state where star formation has largely ceased, and the remaining stars slowly cool and fade. A young galaxy is typically rich in gas, forming stars actively, and often irregular or disturbed in shape. A middle-aged galaxy might be a grand spiral, with ongoing but moderate star formation and a more organized structure. An old galaxy might be a large elliptical, smooth and round, made mostly of old red and yellow stars, with very little gas or ongoing star formation. This progression is sometimes described as galaxies moving from the blue cloud, active, star-forming, blue with young stars, to the red sequence, quiet, settled, glowing with the softer light of older stars. The universe has its own quiet seasons. The transition zone between the blue cloud and the red sequence is sometimes called the Green Valley. Galaxies passing through the Green Valley are in the process of shutting down their star formation. Their star formation rates are declining. Their gas supplies are dwindling. They are slowly transitioning from the active, vibrant stage of galaxy life to the quieter, more settled stage. Astronomers are very interested in galaxies in the Green Valley because they are caught in this transition, neither fully active nor fully quiescent. Studying them helps scientists understand the processes by which star formation is quenched. What exactly causes a galaxy to slow down, to settle, to transition from youthful activity to a quieter maturity? The answers are still being explored, gently and carefully, through the patient work of observation and analysis. One of the processes that can quench star formation in a galaxy is called ram pressure stripping. This happens when a galaxy moves through the hot, diffuse gas that fills the space between galaxies in a cluster. As the galaxy moves, that intergalactic gas acts like a kind of headwind, pushing against the galaxy and slowly stripping away its own gas. Like walking through a light rain, the galaxy loses some of its material as it moves through the cluster environment. Over time, this stripping can remove enough gas from the galaxy that it can no longer form new stars. The galaxy slowly quiets. It becomes redder, older, more settled. Ram pressure stripping is a gentle but relentless process. The environment slowly, patiently, reshaping the galaxy as it moves through the cosmos. Another mechanism that can suppress star formation is called strangulation. It is a softer process than it might sound. In strangulation, a galaxy's supply of fresh gas from outside is slowly cut off, perhaps because it has entered a galaxy group or cluster, where the gas flows that would normally feed it are disrupted. Without a fresh supply of gas, the galaxy can continue forming stars for a while, using the gas it already has. But over time, that gas is depleted and not replenished. Star formation slowly tapers off. The galaxy ages. It is a quiet process, not a sudden dramatic event, but a slow, gentle fading, as the supply of raw material runs out, like a candle burning down to nothing. Slowly, over an immensely long time, gently, without drama, the fire grows smaller and still. Dwarf galaxies are among the most common type of galaxy in the universe. They are small, containing anywhere from a few thousand to a few billion stars, compared to the hundreds of billions. In a large galaxy like the Milky Way, dwarf galaxies come in several varieties: dwarf ellipticals, dwarf irregulars, and dwarf spheroidals. Among others, many of the galaxies in our own local group are dwarf galaxies orbiting around the Milky Way or Andromeda. Dwarf galaxies are fascinating to astronomers because they are relatively simple objects. They have not undergone the complex merging histories of large galaxies, and so they can serve as windows into the early universe. Some of the oldest stars in the universe are found in small dwarf galaxies, stars that have been quietly burning for nearly as long as the universe has existed. One of the most beautiful aspects of astronomy is that looking out into space means looking back in time, Light travels fast, but not infinitely fast. It travels at about 300,000 kilometers per second, and the universe is enormous, so the light we receive from distant objects left those objects long ago. When we look at a star 100 light-years away, we see it as it was 100 years ago. When we look at a galaxy 10 billion light-years away, we see it as it was 10 billion years ago. This means that our telescopes are, in a sense, time machines. We can look at galaxies at different distances and see them at different stages of their evolution. We can compare the young galaxies of the early universe with the mature galaxies of today. We are, in a very real and literal way, seeing the history of the universe written across the sky. Slowly, quietly, the past is still visible. The redshift of a galaxy is one of the most useful tools astronomers have for understanding how far away it is and how the universe has evolved. When a source of light is moving away from us, the light waves are stretched, shifted toward the redder end of the spectrum. This is called a redshift, and it is a consequence of the Doppler effect. The same reason a police siren sounds lower in pitch as it moves away from you. Virtually all distant galaxies show redshift because the universe is expanding, carrying those galaxies away from us. The more redshifted a galaxy's light, the faster it is moving away from us, and the farther away it is. By measuring the redshift of a galaxy, astronomers can calculate how far away it is and how long ago its light left. It is a gentle kind of code, written in the color of light. The expansion of the universe itself is one of the most profound facts in all of science. And yet, it is a quiet, imperceptible thing on human scales. Space itself is slowly stretching. The distance between galaxies is growing, not because they are flying apart through space, in the conventional sense, but because the fabric of space between them is expanding. This was first discovered in the 1920s by astronomers including Edwin Hubble and Vesto Slipher, who noticed that nearly all distant galaxies showed redshift. They were all moving away from us. Hubble realized that the farther away a galaxy was, the faster it appeared to be receding. This became known as Hubble's law. The universe is not static. It is not standing still. It is gently, slowly, but inexorably growing larger with every passing moment. And we, and our galaxy, are along for the ride. Something even more remarkable was discovered in 1998 when two independent teams of astronomers were studying very distant supernovae, exploding stars, to measure the expansion rate of the universe. They expected to find that the expansion was slowing down over time, as the gravity of all the matter in the universe pulled back on itself. Instead, they found the opposite. The expansion of the universe is accelerating. It is speeding up. This discovery won the Nobel Prize in Physics in 2011, and it pointed to the existence of what scientists now call dark energy, a mysterious property of space itself that appears to be driving the accelerated expansion. We do not know what dark energy is, only that it exists, and that it makes up roughly 68% of the total energy content of the universe. Even in the face of the unknown, we can rest in the quiet wonder of discovering something entirely unexpected: the observable universe. The part of the universe whose light has had time to reach us since the Big Bang has a radius of about 46 billion light-years. It contains an estimated 2 trillion galaxies. 2 trillion, each galaxy containing billions, or hundreds of billions of stars, each star potentially surrounded by its own system of planets. The numbers are so large that they cease to feel like numbers and begin to feel more like the quiet hum of vastness itself. And we are here, on one small planet, around one ordinary star, in one spiral arm, of one galaxy among 2 trillion. We can take a quiet moment to notice how small that is, and also how extraordinary that something so small could be aware of something so large that we can sit here softly and think about galaxies being born. The color of a galaxy tells us a great deal about the age and type of stars it contains. Young, massive, hot stars burn blue-white. Older, cooler stars burn yellow, orange, and red. A galaxy that is forming many new, hot, massive stars will appear blue-white overall. A galaxy that has stopped forming new stars and now contains mostly old stars will appear more yellowish or reddish. Our own Milky Way is somewhere in the middle. It is both young blue stars and older yellow and red stars. When astronomers classify galaxies by color, they can get a sense of how actively the galaxy is forming stars and how old its stellar population is. It is a gentle kind of reading, the universe writing its own biography in color across the sky. For those patient enough to look and listen, a light year is not a unit of time, despite what the name might suggest. It is a unit of distance, the distance that light travels in 1 year. Light travels about 9.46 trillion kilometers in a year. So 1 light year is about 9.46 trillion kilometers. The nearest star to our Sun, Proxima Centauri, is about 4.2 light years away. That means it is about 40 trillion kilometers from us. The Milky Way is about 100,000 light years across, and the nearest large galaxy, Andromeda, is about 2.5 million light years away. These distances are so vast that they resist ordinary comprehension. But there is something comforting about that, something deeply peaceful, about the immensity of the universe, about the fact that these distances are so large. They can never be rushed. There is nowhere we could be in a hurry to get to. The universe is simply vast, and vast things move slowly. The Milky Way's spiral arms are not spinning like the spokes of a wheel. This is a common misconception. If they were, the arms would wind up tighter and tighter over time, and eventually disappear, which would happen on a relatively short astronomical timescale. Instead, the spiral arms are density waves, regions of slightly higher density, that rotate through the disk of the galaxy, more slowly than the stars themselves. Stars enter the arms, slow down slightly, become more crowded, and then pass through, and continue on their way. It is a little like a slow-moving traffic jam on a highway. The jam itself moves at a different speed from the individual cars within it. The spiral pattern is a traveling wave in the stellar disk, not a fixed structure. It is a slow, beautiful, rolling pattern, a wave passing through a galaxy, gently, endlessly. The globular clusters that orbit our Milky Way are some of the oldest objects in the universe. A globular cluster is a dense, spherical collection of stars, sometimes containing hundreds of thousands of stars, packed closely together, that orbits the center of the galaxy, in a long, slow, looping path. The Milky Way has over 150 known globular clusters. Many of them contain stars that are over 12 billion years old, nearly as old as the universe itself. When we look at a globular cluster, we are looking at stars that formed in the early universe, long before our Sun existed, long before Earth existed. They have been quietly orbiting ever since, surviving through billions of years of cosmic change. There is something deeply peaceful about that kind of age, that kind of quiet persistence. The stellar halo is a faint, roughly spherical component of the Milky Way that surrounds the disk. It is made up of old stars, globular clusters, and streams of stars torn from smaller galaxies that fell into the Milky Way long ago. It is sparse. The stars in the halo are much more spread out than those in the disk, but it extends to enormous distances, perhaps 130,000 light-years from the center or more. The halo contains some of the oldest and most metal-poor stars in the galaxy, stars made mostly of hydrogen and helium, with very little of the heavier elements that would come later. These are ancient stars, They formed before the galaxy had time to enrich itself with the heavier elements, produced in stellar interiors and supernova explosions. They are, in a sense, relics, the quietly glowing remnants of the galaxy's earliest days. The center of the Milky Way is in the direction of the constellation Sagittarius. As seen from Earth, on a clear, dark night, far from city lights, the central bulge of the Milky Way appears as a brighter, denser region of the band of light that arches across the sky, but we cannot actually see all the way to the galactic center with visible light because there is too much dust and gas in the way. The dust absorbs and scatters the light. To peer into the center of the galaxy, astronomers use infrared light, radio waves, and X-rays, which can pass through the dust more easily. When they do, they find a dense, busy region, a tight cluster of stars, orbiting very close to Sagittarius A*, the central black hole. Some of those stars complete an orbit around the black hole in just a few years, traveling at remarkable speeds. And yet, even that is a slow orbital dance at its heart. Our Sun has been orbiting the center of the Milky Way since it was born, approximately 4.6 billion years ago. It takes the Sun roughly 225 to 250 million years to complete one full orbit around the galactic center. This unit of time is sometimes called a cosmic year or a galactic year. In the 4.6 billion years since the Sun was born, it has completed about 18 to 20 galactic orbits. The last time our solar system was in the same position in the galaxy as it is today, the most complex life on Earth, was early dinosaurs. The time before that, there was almost no complex life at all, and we can take a quiet moment to notice how slowly the galaxy turns, how patient its rhythms are. One orbit every 225 million years, quietly, steadily, carrying us along. The disk of the Milky Way is not perfectly flat. It is slightly warped, bent, like a gently curved vinyl record. Scientists have known about this warp for decades. More recent observations have confirmed that the warp is actually slowly precessing, rotating over time, likely due to the gravitational influence of the Large and Small Magellanic Clouds, the two satellite galaxies of the Milky Way. This gentle bending and slow rotation of the galactic disk is another reminder that the galaxy is not a static object. It is dynamic and slowly changing, responding to the gravitational influences of the objects around it. Even at this enormous scale, the universe is still in motion, still slowly adjusting, still quietly becoming. There are regions of the Milky Way where star formation is currently very active. The most famous of these is the Orion Nebula, which is visible to the naked eye as a faint fuzzy patch within the constellation Orion. The Orion Nebula is a stellar nursery, a large cloud of gas and dust, where new stars are actively forming right now. It is about 1,344 light-years from Earth, and about 24 light-years across. Within it, astronomers have found thousands of young stars, in various stages of formation, including many with protoplanetary disks around them, disks that may one day give birth to planets. The Orion Nebula is one of the most studied objects in the sky, and one of the most beautiful, a place where the universe is still, gently and slowly, making new suns. Beyond the Milky Way's familiar spiral disk, there exists a vast, diffuse region, called the circumgalactic medium. This is a halo of warm, tenuous gas that surrounds the galaxy and extends far beyond the visible disk, perhaps a few 100,000 light-years. In every direction, the circumgalactic medium plays an important role. In the galaxy's life cycle, it acts as a reservoir of gas that can slowly flow inward to replenish the galaxy's star-forming material, and it also receives gas that is blown outward by stellar winds and supernova explosions. Scientists are still working to understand the circumgalactic medium fully, because it is very diffuse and hard to observe, but it is clear that this vast, quiet atmosphere surrounding the galaxy is an important part of the overall system, like a slow-breathing envelope of gas, gently exchanging material with the galaxy within. When astronomers look at very deep images of the sky, images that have collected light for many hours, or even days, they find that essentially every point of light, every faint smudge in the darkest parts of the sky, is a galaxy. The Hubble Deep Field images, taken in the 1990s, were some of the first to really demonstrate this. The Hubble Space Telescope was pointed at a tiny, apparently blank patch of sky, a region about the size of a grain of sand, held at arm's length, and collected light for about 10 days. The result was an image containing about 3,000 galaxies. Every smear of light, a galaxy, each one containing billions of stars. In a patch of sky so small, it is essentially nothing. The depth and richness of the universe is quietly, completely staggering. The Hubble Ultra Deep Field, taken between 2003 and 2004, went even deeper. It revealed about 10,000 galaxies, in a patch of sky about a tenth of the diameter of the full moon. Some of those galaxies are seen as they existed when the universe was only about 800 million years old. They are among the most distant objects ever imaged. Looking at the Hubble Ultra Deep Field is a meditation. It is a quiet confrontation with the sheer scale of the cosmos. Every point of light in that image is not a star. It is an entire galaxy, a collection of billions of stars. Looking at it, there is a kind of vertigo, a gentle dizziness from the scale of it, and then a deep, settling calm. The universe is so large, and we are somehow here within it. The James Webb Space Telescope has now surpassed even the Hubble's deep field images. With its larger mirror and its sensitivity to infrared light, Webb can see farther back in time than any previous instrument. Some of the galaxies Webb has imaged appear as they existed when the universe was only about 300 to 500 million years old. The very earliest galaxies, and they look different from the galaxies we see today. They are smaller, less structured, more irregular. They are the raw, early forms of galaxies, still in the process of assembling themselves. Looking at them is like looking at old photographs, at something very young and very ancient at the same time. The universe, at its own earliest age, slowly coming into focus across 13 billion years of time and space. One of the most distant galaxies known, as of recent observations, was seen as it existed when the universe was only about 320 million years old. Its light has been traveling toward us for about 13.5 billion years. That light left its source before the Earth existed, before the Sun existed, before most stars in the Milky Way existed. It has been crossing the universe for all of that time, quietly, at the speed of light, until finally it arrived at our telescope, and we could look at it and learn something about the very earliest galaxies. There is something very moving about that, if we let ourselves feel it gently. That ancient light, having traveled so far and so long, quietly carrying its information across the vastness of space. To reach us here, astronomers classified the age of a galaxy's stars using something called metallicity. In astronomy, the word metal refers to any element heavier than hydrogen and helium. So oxygen, carbon, iron, silicon, all of these are metals in the astronomical sense. Even though most of them are not metals, in the everyday chemical sense, stars that formed early in the universe contain very little of these heavier elements. They are called metal poor, or low metallicity stars, stars that formed more recently, from gas that had been enriched by many generations of previous stars, contain more of these heavier elements. They are metal-rich. By measuring the metallicity of a galaxy's stars, astronomers can get a sense of how many generations of stellar evolution that galaxy has gone through. It is like reading the age of a tree by counting its rings. The universe keeps its own quiet record of time. Cosmic voids are the large, empty regions of space. Between the filaments of the cosmic web, they can span hundreds of millions of light years. Within voids, galaxies are very sparse. The density of matter is much lower than average. If you were somehow transported to a random location inside a large cosmic void, the night sky would be much darker and lonelier than our own. There would be far fewer galaxies visible in any direction. And yet, voids are not completely empty. There are galaxies there, just very few of them. Scientists call these lonely outliers void galaxies, and they are interesting because they have evolved in very different environments. From galaxies embedded in dense clusters or filaments, they have generally had quieter lives, fewer mergers, fewer disturbances. They have been able to evolve more calmly. In their quiet corners of the cosmos, galaxy clusters are the largest gravitationally bound structures in the universe. A large galaxy cluster can contain hundreds or even thousands of individual galaxies, all bound together by gravity and embedded in an enormous cloud of very hot diffuse gas called the intercluster medium. The intercluster medium is so hot, tens of millions of degrees, that it emits X-rays, which astronomers can detect with space-based X-ray telescopes. The total mass of a galaxy cluster is dominated not by the galaxies themselves, nor even by the hot gas, but by dark matter, invisible material that provides most of the gravitational glue, holding the cluster together. Some of the most detailed evidence for the existence of dark matter comes from studies of galaxy clusters. Quietly, invisibly, dark matter holds the largest structures in the universe together. The Coma cluster is one of the nearest large galaxy clusters to us. Located about 320 million light-years away, it contains over 1,000 galaxies, most of them ellipticals and lenticulars. It was one of the first objects to provide evidence for dark matter. In the 1930s, astronomer Fritz Zwicky measured the velocities of galaxies within the Coma cluster and found that they were moving far too fast for the visible mass of the cluster to hold them together. He concluded that there must be some additional, invisible mass, dark matter, providing the extra gravitational pull. This was one of the earliest hints of dark matter's existence. It was quietly there in the data for decades before the evidence became overwhelming. The universe patient with its secrets, revealing them slowly to those who looked carefully and without hurry. The Virgo cluster is the nearest large galaxy cluster to us. Located about 54 million light-years away, it contains over 1,300 galaxies and has a total mass of roughly 1.2 quadrillion solar masses. The Virgo cluster is the dominant structure in our local region of the universe, and the gravity of the Virgo cluster is actually slowing the expansion of our local group slightly, pulling us, very gently, in its direction. We are not falling into the Virgo cluster, but we are moving slightly more slowly away from it than we would be if it were not there. Even on the scale of galaxy clusters, gravity works its patient, quiet influence. No drama, no urgency, just a gentle, persistent pull across tens of millions of light-years. Some of the most energetic events in the universe, gamma-ray bursts, are associated with certain types of galaxies and can be detected across enormous distances. Gamma-ray bursts are brief, but extraordinarily intense flashes of high-energy radiation. They come in two varieties: long gamma-ray bursts, which are associated with the collapse and explosion of very massive stars, and short gamma-ray bursts, which are associated with the merger of two neutron stars, or a neutron star and a black hole. When two neutron stars merge, they can produce something called a kilonova, an explosion that forges many of the universe's heaviest elements, including gold, platinum, and uranium. So the gold in a piece of jewelry on Earth was almost certainly forged in the violent merger of two dead stars billions of years ago. Slowly, gently, those atoms made their way here, to this small world, to this quiet moment. Stars within a galaxy move on orbits around the galactic center, just as planets orbit a star. But the orbits of stars in a spiral galaxy are generally much more circular than the highly elongated orbits of comets around a sun. Stars in the disk of the Milky Way, like our own sun, follow roughly circular orbits in the plane of the disk, gently bobbing up and down through the plane as they go. Stars in the galactic halo follow much more elongated, randomly oriented orbits, looping far above and below the disk. Before returning, these different orbital patterns reflect the different histories of disk stars and halo stars. Disk stars formed from rotating gas clouds and inherited that rotation. Halo stars are ancient, formed before the disk settled into its current shape, each one quietly carrying the memory of its formation. In the pattern of its orbit, the Sun is a relatively ordinary star, medium in mass, middle-aged in cosmic terms. It is classified as a G-type main sequence star, or sometimes informally called a yellow dwarf. It is about 4.6 billion years old, and has roughly another 5 billion years of hydrogen-burning life ahead of it. By mass, the Sun is about 70% hydrogen and 28% helium, with the remaining 2% made up of heavier elements. It fuses about 600 million tons of hydrogen into helium every second in its core. And yet, this extraordinary process unfolds quietly and steadily. The Sun does not pulse or flare dramatically. In its main activity, it simply burns, day after day, year after year, billion after billion of years. A steady, warm, patient light. Exactly what a small planet full of life needs. The most common type of star in the galaxy is not a star like our Sun. It is a smaller, cooler, dimmer star, called a red dwarf, or M-type star. Red dwarfs are far less massive than the Sun, typically between about 8 and 60% of the Sun's mass. They burn their fuel much more slowly, and live much, much longer. While the Sun will live for about 10 billion years, a red dwarf can live for tens to hundreds of billions of years. The smallest red dwarfs may live for trillions of years, far longer than the current age of the universe. There are no old red dwarfs that have already died, because none have had time to. They're still all living, quietly, burning their fuel with incredible patience. They make up somewhere around 70 to 75% of all the stars in the Milky Way. The universe is, in its majority, quiet and dim, and very long-lived. At the other end of the stellar mass scale are the giant stars, blue supergiants and hypergiants. These are extraordinarily massive stars, sometimes containing 50, 100, or even more times the mass of the Sun. They burn their fuel at a furious rate and live for only a few million years before dying in spectacular supernova explosions. Despite their short lives, these massive stars have an outsized influence on their surroundings. Their intense radiation and stellar winds can carve out enormous cavities in surrounding gas clouds, reshaping the environments in which they live. They are like brilliant, brief flames, burning fiercely and briefly. And when they die, they seed the galaxy with the heavy elements they forged in their interiors. Brief, bright, generous lives, and then gone, leaving their gifts behind. In the slowly drifting gas, when a star like our Sun reaches the end of its hydrogen-burning life, it will swell into a red giant, eventually expanding to perhaps 100 times its current size. At that point, it will be large enough to engulf the inner planets of the solar system. But this expansion happens very slowly, over millions of years. It is not a sudden or violent event. After the red giant phase, the outer layers of the Sun will be gently blown away, forming a beautiful shell of gas, called a planetary nebula. The core left behind will become a white dwarf, a small, dense, cooling remnant, about the size of Earth, made mostly of carbon and oxygen. Over billions of years, that white dwarf will slowly cool and fade. Eventually, it will become cold and dark, a black dwarf, though the universe is not yet old enough for any white dwarf to have fully cooled into a black dwarf. They are still all quietly glowing. Emission nebulae are among the most colorful and beautiful objects in the galaxy. They are clouds of gas, mostly hydrogen, that have been energized by the ultraviolet light of nearby hot, young stars. The ultraviolet light strips electrons from the hydrogen atoms, and when those electrons recombine with the atoms, they release energy as visible light. The most famous color in emission nebulae is a deep, rich red, the red of hydrogen alpha emission. This is the color that makes images of nebulae, like the Eagle Nebula or the Carina Nebula, so iconic. But emission nebulae also glow with greens and blues from other elements, like oxygen and sulfur. They are the colors of newborn stars, illuminating the gas clouds from which they emerged, still glowing softly. In the early light of new creation, reflection nebulae are different from emission nebulae. Rather than glowing with their own light, they shine by reflecting the light of nearby stars. They tend to appear blue because dust particles scatter blue light more efficiently than red light. The same reason Earth's sky is blue. The Pleiades star cluster is surrounded by a beautiful blue reflection nebula, visible in long-exposure photographs. The dust is not associated with the Pleiades themselves. The cluster is simply passing through a cloud of interstellar dust, and the light of the bright young stars illuminates it. It is a temporary chance encounter between a star cluster and a passing cloud, two travelers meeting briefly in the dark, the cluster lighting up the dust cloud, like headlights in fog, and then both moving slowly on. Dark nebulae are clouds of dense gas and dust that block the light from stars and other objects behind them. Rather than glowing or reflecting, they simply absorb. They appear as dark patches against the brighter background of the Milky Way, or a bright emission nebula. The most famous dark nebula is probably the Horsehead Nebula in Orion, a dense cloud of dust shaped very gently and very approximately like the silhouette of a horse's head, set against the glow of a bright emission nebula behind it. Dark nebulae are important. They are dense and cold, and they are often the places where new stars are forming, hidden from view. Within their dusty depths, the darkness is not emptiness. It is often fullness, density, the quiet, unseen beginning of new stars. Supernova remnants are another beautiful type of nebula. When a massive star explodes as a supernova, it blasts its outer layers outward at enormous speeds, typically thousands of kilometers per second, as this expanding shell of gas plows through the surrounding interstellar medium. It heats the gas it encounters to millions of degrees, causing it to glow. Over thousands of years, the remnant expands and cools, eventually fading. The Crab Nebula is one of the most famous supernova remnants, the product of a supernova that was observed by Chinese astronomers in the year 1054 CE, nearly 1,000 years ago. Today it spans about 11 light years and is still expanding At its center is a rapidly spinning neutron star, a pulsar, the beautiful, still expanding consequence of an ancient stellar death, quietly spreading its material across space. Planetary nebulae, despite their name, have nothing to do with planets. They were named by early astronomers, who thought they looked somewhat like planets. Through small telescopes, they are actually the expelled outer layers of dying sun-like stars, beautiful shells of luminous gas, surrounding the hot, fading core of the star. They come in a remarkable variety of shapes. Some are nearly perfect spheres. Others are bipolar, shaped like hourglasses or butterflies. The Ring Nebula in the constellation Lyra is a classic example, visible as a small, glowing ring through a backyard telescope. These are very transient objects. They glow for only about 10,000 years before fading into the interstellar medium. A brief, beautiful luminosity, a quiet last exhalation of a star that has finished its long life. Between the stars, space is not truly empty. It is filled with a very tenuous mixture of gas and dust, called the interstellar medium. The density of the interstellar medium is extraordinarily low, far lower than the best vacuum that can be created in a laboratory on Earth. In some regions, there may be only about 1 atom per cubic centimeter, compared to the air in this room, which contains about 2.7 times 10 to the power of 19 molecules per cubic centimeter. The interstellar medium is almost incomprehensibly sparse. And yet, because the galaxy is so vast, the total amount of material in the interstellar medium is enormous. It contains gas and dust that will one day form new stars. It is the raw material of the future, drifting quietly through the galaxy, waiting patiently for gravity to gather it together once more. The interstellar medium is not uniform. It exists in several different phases, each with different temperatures and densities. There is the hot ionized medium, extremely hot, low-density gas, heated by supernova explosions and stellar winds. There is the warm ionized medium, slightly cooler and denser. There is the warm neutral medium, and the cold neutral medium, made of neutral hydrogen atoms. And there are molecular clouds, the coldest, densest regions, where hydrogen exists in molecular form as H2, and where temperatures can drop to just a few degrees above absolute zero. These cold molecular clouds are the nurseries where new stars form. The coldest, quietest regions of the galaxy are where the next generation of stars is slowly gathering itself. Cold, dense, dark, and quietly creative. Interstellar dust, which makes up only about 1% of the interstellar medium by mass, plays an outsized role in the chemistry and physics of galaxies. Dust grains are tiny, typically about 1/10 of a micrometer across, roughly 1,000 times smaller than a grain of beach sand. They are made of silicates, carbon compounds, and ice. They absorb and scatter starlight, causing distant stars to appear dimmer and redder than they actually are. But they also serve as a surface on which complex chemistry can occur. Atoms of hydrogen and other elements can stick to the surface of a dust grain and react together, forming more complex molecules. Many of the organic molecules found in molecular clouds, including some amino acid precursors, likely formed on dust grain surfaces. Even in the cold dark between the stars, chemistry is slowly, quietly at work. The interstellar medium is continuously being recycled. Stars form from it. They burn for millions or billions of years. They shed material through stellar winds throughout their lives, and when they die, either quietly as planetary nebulae or dramatically as supernovae, they return most of their material back to the interstellar medium, enriched with the heavier elements they forged during their lifetimes. That enriched gas then drifts through the galaxy, mixes with other gas, eventually cools and condenses into new molecular clouds, and the cycle begins again. The next generation of stars contains slightly more heavy elements than the previous one, and the generation after that, slightly more still. A slow, patient enrichment. The galaxy building complexity, one stellar generation at a time. Quietly, without hurry, magnetic fields permeate the interstellar medium of the Milky Way. These fields are very weak by everyday standards, roughly a few microgauss, compared to the Earth's magnetic field of about half a Gauss, but they play an important role in the dynamics of the galaxy. They thread through gas clouds, helping to support them against gravity and slowing down the collapse that leads to star formation. They influence the motion of cosmic rays, high-energy charged particles that zip through the galaxy. They help shape the large-scale structure of the interstellar medium. Magnetic fields are invisible, and their effects are subtle, but they are omnipresent and important. Another quiet, invisible force, shaping the galaxy alongside gravity. The universe is woven through, with invisible influences, gently guiding matter across enormous scales. Many large galaxies, including our own Milky Way, are surrounded by smaller satellite galaxies, dwarf galaxies, that orbit the larger galaxy under its gravitational influence. The Milky Way has over 50 known satellite galaxies, most of them very small, and faint dwarf galaxies. The two most prominent are the Large Magellanic Cloud and the Small Magellanic Cloud. These two small, irregular galaxies are visible to the naked eye from the southern hemisphere, looking like detached wisps of the Milky Way. They are about 160,000 and 200,000 light-years away, respectively. They are gravitationally bound to the Milky Way and are slowly orbiting around it. In the distant future, they will likely be drawn in and eventually merge with the Milky Way, as many satellite galaxies have done before them. The Magellanic Stream is a long ribbon of hydrogen gas that stretches from the Magellanic Clouds across a large arc of the sky. It was drawn out of the Magellanic Clouds by tidal forces from the Milky Way. As the clouds move through their orbit, the stream spans over 300 degrees of the sky, more than half the way around, making it one of the largest structures associated with our galaxy. It is very faint and invisible to the eye, but detectable in radio waves. The Magellanic Stream is a gentle reminder of the gravitational interaction between the Milky Way and its satellite galaxies. Gravity, reaching across hundreds of thousands of light-years, slowly pulling tendrils of gas from one object to another, patiently, over millions of years, shaping the distribution of material around our galaxy. Andromeda, our nearest large galactic neighbor, also has its own system of satellite galaxies. It has at least 14 known satellite galaxies, including M32 and M110, which are visible in small telescopes as faint companions to Andromeda itself. The satellite system around Andromeda shows some interesting patterns. Many of the satellites appear to be arranged in a thin rotating plane, rather than distributed randomly in 3 dimensions. This is a puzzle for galaxy formation theorists who are still working to understand how such organized structures arise. When we observe the beautiful photographs of Andromeda, that grand, slightly tilted spiral disk, with its hazy central glow, we are looking at our future. In about 4 billion years, the Milky Way and Andromeda will be beginning their slow, gentle merger. The two great spirals of the local group, slowly becoming one. Stellar streams are thin ribbons of stars, stretched out along the orbit of a satellite galaxy or globular cluster that is being disrupted by the gravity of its host galaxy. As a satellite galaxy or globular cluster orbits around the Milky Way. Tidal forces, differences in the strength of gravity, across the object, slowly pull stars from the leading and trailing edges of the satellite, stretching them out along the orbit. Over millions of years, a beautiful, thin arc of stars develops, tracing the orbital path. Our galaxy is surrounded by several known stellar streams: the Sagittarius stream, the Orphan stream, and others. They are like the quiet wakes left by objects as they move through the gravitational field of the galaxy. Whisper-thin traces of past orbits, slowly spreading and fading into the halo. The local group of galaxies, the collection that includes the Milky Way, Andromeda, and their associated smaller galaxies, is held together by its own mutual gravity. Even though the universe is expanding and carrying most distant galaxies away from us, the local group is gravitationally bound. Its members will not be carried apart. By cosmic expansion, they will remain together, orbiting, and eventually merging over the next several billion years. Beyond the local group, the nearest galaxy groups are being carried away from us. By cosmic expansion, we are, in a sense, in our own small gravitational community, a quiet neighborhood in the vastness of the cosmos, bound together, slowly orbiting, slowly merging, in our own corner of the universe, gently, across deep time. The universe has a timeline that is helpful to hold gently in mind. In the first second, after the Big Bang, the fundamental particles and forces that make up everything were established. In the first 3 minutes, the lightest atomic nuclei, hydrogen, helium, and a tiny bit of lithium, were formed. By 380,000 years, the first atoms formed, and the universe became transparent, releasing the cosmic microwave background. Between roughly 200 million and 500 million years, the first stars and galaxies began to form. By about 1 billion years, the universe was increasingly populated with young, active galaxies. By about 9 billion years, about 4.6 billion years ago, our own sun formed. And now, 13.8 billion years after the beginning, we are here, looking back at all of it, sitting quietly with the whole long, slow, extraordinary story. The epoch of reionization is a fascinating period in the universe's early history. After the cosmic dark ages, when the first stars and galaxies began to form, they emitted ultraviolet radiation that slowly ionized the surrounding hydrogen gas, clearing the cosmic fog. This process, reionization, is thought to have begun about 150 to 200 million years after the Big Bang, and was largely complete by about 1 billion years. During this period, the universe transitioned from being filled with neutral hydrogen gas, which blocks certain wavelengths of light, to being filled with ionized hydrogen plasma, which is largely transparent. This transition fundamentally changed the character of the universe. The cosmic fog lifted. Light could travel freely. The universe, which had been largely opaque, became clear. A slow, long dawn, spreading across the cosmos over hundreds of millions of years. Quasars were extraordinarily luminous objects that were very common in the early universe, but are much rarer today. They are now understood to be active galactic nuclei, the bright, energetic centers of galaxies, where a supermassive black hole is consuming material at a very high rate. The accretion disk of gas, swirling around the black hole, heats up to extreme temperatures and releases tremendous amounts of energy, sometimes outshining the entire rest of the galaxy by a factor of 100 or more. Quasars were first discovered in the 1950s and 60s as point-like radio sources that turned out to be extraordinarily far away, meaning they were incredibly luminous. They provide us with bright beacons in the early universe, allowing astronomers to probe the conditions of the young cosmos, blazing lights from the beginning of time, still reaching us across the expanding universe. Blazars are a type of active galaxy in which a powerful jet of material is pointed almost directly toward Earth. A blazar is essentially a quasar, seen from a very specific angle. With the jet aimed right at us, the jet produces intense radiation across all wavelengths, from radio waves to gamma rays. Blazars are some of the most energetic objects in the known universe, and yet they're far away, very, very far away. Their energy reaches us, diluted across billions of light years of space. By the time their radiation arrives at Earth, it is harmless, a faint signal, easily detected only by sensitive instruments. The universe can contain extraordinary violence at a great distance, and that great distance means we are entirely safe, entirely peaceful. We can study these distant beacons calmly, curiously, from the quiet comfort of this small and distant world. Radio galaxies are another type of active galaxy in which the central black hole produces powerful jets that extend far beyond the visible galaxy itself. These jets travel at close to the speed of light and can extend for millions of light years, eventually spreading out into enormous clouds of radio-emitting plasma called radio lobes. The largest radio galaxies have radio lobes spanning many millions of light years, the largest single structures in the universe. These enormous jets and lobes are driven by the energy of the accreting black hole. They heat the gas in the surrounding galaxy cluster, preventing it from cooling and forming stars. Even at these enormous scales, the feedback between black holes and their environments plays out quietly, shaping the evolution of large-scale structure across deep time. In the very distant future, the fate of galaxies will be shaped by the continued expansion of the universe. Dark energy is causing the expansion to accelerate. Galaxies that are not gravitationally bound to each other, which means galaxies beyond our local group, are being carried away from us at ever-increasing speeds. In a few billion years, the nearby universe will look similar to what it does today, but on much longer timescales. The observable universe will appear to shrink as more and more galaxies are carried beyond the cosmological horizon, the distance beyond which the expansion of space is so fast that light from those galaxies can never reach us. Eventually, the observable universe, as seen from the Milky Way, or whatever the Milky Way will have become, will contain only the local group. The rest of the universe will have faded silently away behind an expanding horizon. In about 5 billion years, the merger of the Milky Way and Andromeda will be underway. The resulting galaxy, sometimes called Milkomeda, will likely be a large elliptical galaxy. The Sun, if it still exists at that point, it will be nearing the end of its life, will probably be in a completely different position within the merged galaxy than it is today. The nights on any planet orbiting the Sun at that distant time would be extraordinary. The sky would be lit by the combined light of two merging galaxies, streams of stars across the sky, a bright, diffuse central glow, and the scattered remnants of two former spirals, slowly settling into one smooth, rounded form. The universe will look very different, slower, quieter, more settled. the grand spirals of our youth, transformed into the calm elliptical of old age in the very far future, on timescales of trillions to quadrillions of years. Stars themselves will begin to die out. The long-lived red dwarf stars will burn on for trillions of years, but eventually, even they will exhaust their fuel and fade. The last stars will cool and darken. The universe will enter what cosmologists call the degenerate era, a long, quiet period where the universe consists mostly of brown dwarfs, white dwarfs, neutron stars, and black holes slowly cooling. In the dark, this is not a sad thought. It is a very long way away, and it is, in its own way, a peaceful image, an enormous universe, growing slowly darker and quieter, returning to something like the darkness from which it began, the long, slow exhalation at the end of a very, very long day. Even black holes do not last forever. Stephen Hawking theorized in 1974 that black holes slowly emit a faint radiation, now called Hawking radiation, due to quantum mechanical effects near the event horizon. This radiation carries away energy from the black hole, causing it to very, very slowly shrink over an extraordinarily long time. For a stellar mass black hole, something like 10 to the power of 67 years, and for a supermassive black hole, something like 10 to the power of 93 years. The black hole would eventually evaporate completely. These timescales are so enormous that they make the current age of the universe seem like a brief opening moment, but nothing is permanent. Even the darkest, most patient things in the universe quietly, slowly, eventually dissolve. Everything in the universe, given enough time, returns to the gentle openness of the cosmos. Neutron stars are among the most extraordinary objects in the universe. They are the collapsed cores left behind after certain types of supernova explosions, objects with about 1.4 to 2 times the mass of the Sun, packed into a sphere only about 20 kilometers across. The density inside a neutron star is almost incomprehensible. A teaspoon of neutron star material would weigh about 4 billion tons. On Earth, the pressure is so extreme that electrons and protons are forced together to form neutrons, giving the object its name. Neutron stars can spin extremely rapidly, sometimes hundreds of times per second, and some emit beams of radio waves that sweep around like lighthouse beams. These are called pulsars. They are extraordinarily precise clocks, quietly ticking hundreds of times per second. In the dark, the universe contains approximately 2 trillion galaxies, as we mentioned gently earlier, but the distribution of galaxy sizes is very uneven. The vast majority, perhaps 90% or more, are dwarf galaxies, small and faint. Large galaxies, like the Milky Way, are actually a minority. The average galaxy contains far fewer stars than the Milky Way. This is a gentle reminder that what we think of as typical is often not typical at all. The large, bright, beautiful spiral galaxies that dominate astronomical imagery are actually relatively rare. Most galaxies are small, quiet, dim collections of stars orbiting larger galaxies or drifting quietly in the spaces between. The universe is mostly full of small, quiet things, and there is something very reassuring about that. The large-scale structure of the universe, the pattern of filaments, walls, clusters, and voids that makes up the cosmic web is one of the most remarkable discoveries of modern cosmology. On scales of hundreds of millions of light years, the universe has a definite structure. Galaxies are not uniformly distributed. They cluster along filaments and at the intersections of filaments with vast empty regions between. This structure grew from the tiny fluctuations in the early universe, the tiny temperature differences in the cosmic microwave background, amplified over billions of years by gravity. The cosmic web is, in a very real sense, the large-scale memory of the universe's earliest moments. The patterns, set down in the first fractions of a second after the Big Bang, slowly amplified and grown into the structures we see today across hundreds of millions of light years. When galaxies collide, the stars within them almost never physically collide with each other. This is because the distances between stars within a galaxy are enormous compared to the sizes of the stars themselves. If you shrank the sun to the size of a marble, about a centimeter across, the nearest star would be another marble, about 280 kilometers away. The space between them is extraordinarily vast. When two galaxies merge, the stars pass through each other's stellar populations, like two swarms of bees, merging with enough space between individuals that actual collisions are extremely rare. What has changed dramatically is the distribution of gas. Gas clouds can and do collide, compress, and trigger massive star formation. The stars simply drift through each other, their orbits distorted by the changing gravity, slowly settling into new patterns. In the merged galaxy, the oldest stars in the universe are found in the halos and globular clusters of galaxies, the oldest known individual star observable, sometimes called Methuselah's star, officially designated HD 140283, is estimated to be approximately 13.7 billion years old, give or take a few hundred million years. It is a metal-poor subgiant star, about 190 light-years from Earth, drifting through the halo of the Milky Way on a looping orbit. It formed very early in the universe's history from gas that had barely been enriched by previous generations of stars. It has been burning quietly for nearly 14 billion years, older than the Earth by many billions of years, quietly present, quietly burning, a living connection to the universe's earliest moments. Stars communicate with each other only through the slow exchange of gravity, light, and the drifting of the interstellar medium over immense timescales. In a very loose sense, every star in the galaxy is connected to every other star through the shared gravitational field of the galaxy as a whole. The movements of stars, the births of new stars, from shared gas clouds, the heavy elements returned to the interstellar medium from dying stars, all of these create a kind of slow, ongoing exchange of material and influence across the galaxy. The Milky Way is not a collection of isolated points of light. It is a living, slowly changing ecosystem. Material flows through it. Energy moves through it. Every star is, in some small way, shaped by the existence of all the others. Quietly, gently, across hundreds of thousands of light years, the color of a star is intimately connected to its surface temperature. Blue stars are the hottest, with surface temperatures of 30,000 degrees Celsius or more. White stars are slightly cooler. Yellow stars, like our sun, have surface temperatures around 5,500 degrees Celsius. Orange and red stars are cooler still. The coolest true stars have surface temperatures of only about 2000 to 3000 degrees Celsius. This relationship between temperature and color is a fundamental law of physics. All hot objects emit light, and the color of that light depends on the temperature. It is called blackbody radiation. The stars are not colored for decoration. They are colored by their physics. The universe does not choose colors for beauty, but beauty emerges from the underlying laws. Regardless, the night sky is a soft spectrum, each colored point of light quietly announcing its own temperature. The speed of light, about 299,792 kilometers per second, is the ultimate speed limit of the universe. Nothing can travel faster than light through space. This has a profound implication for our ability to communicate across cosmic distances. Even a message sent from Earth to Proxima Centauri, our nearest stellar neighbor, would take 4.2 years to arrive. A message to the center of the Milky Way would take 26,000 years. A message to Andromeda would take 2.5 million years. At cosmic scales, communication becomes impossibly slow by human reckoning. And yet, there is something beautiful about this limitation. The universe does not rush. Its information travels at the speed of light, the fastest possible, and still extraordinarily slow, across the vast, quiet distances of space. The universe imposes its own gentle patience on all things. The Milky Way contains a great deal more gas in its outer regions than was previously thought. Recent observations have revealed enormous amounts of warm and hot gas extending far beyond the visible disk of the galaxy. This extended gas reservoir is part of the circumgalactic medium we discussed earlier. The total mass of gas in this extended halo may be comparable to the mass of all the stars in the Milky Way. This reservoir of gas represents a potential future supply of star-forming material for the galaxy. If it cools and falls inward over the coming billions of years, it could fuel continued star formation in the Milky Way long into the future. The galaxy, it seems, has more resources than we knew, more material in reserve, a quiet abundance gently waiting at its outer edges. The relationship between galaxy mass and the number of stars it contains is not straightforward. Larger galaxies do not simply have proportionally more stars than smaller ones. The efficiency with which galaxies convert gas into stars varies with galaxy mass and is actually quite low across the board. Even in active, star-forming galaxies, only a small fraction of the available gas is actually converted into stars at any given time. The rest is stored in the interstellar medium, blown out by stellar feedback, or simply left unused. This low efficiency of star formation is one of the important constraints that galaxy formation models must explain. The universe, it turns out, is quite inefficient at turning gas into stars, and that inefficiency is actually crucial. It is why galaxies can sustain star formation for billions of years, rather than converting all their gas into stars in one great burst, and then going dark. The chemical evolution of galaxies is a beautiful, slow process. As each generation of stars lives and dies, it enriches the interstellar medium, with heavier elements, the very first generation of stars, population 3 stars, formed from gas that was essentially pure, hydrogen and helium. The second generation, population 2 stars, which include most of the stars in the galactic halo and globular clusters, formed from gas, slightly enriched by the explosions of those first stars. The third generation, population 1 stars, which include our Sun, formed from gas that had been enriched by many previous generations. Each generation of stars inherits the chemical legacy of all those that came before. The universe is slowly growing richer in complexity, one stellar generation at a time, quietly, without fanfare. There are regions of the universe where no galaxy has ever formed, and these regions are called cosmic voids. The largest known void is the Boötes void, located about 700 million light-years away. It is approximately 330 million light-years in diameter, an enormous, nearly empty region of space. Inside the Boötes void, there are only about 60 known galaxies, compared to the thousands that would be expected in a region of that size. The void was discovered in 1981 and remains one of the largest known structures in the universe. What caused it to be so empty is not fully understood, but it is simply there, a vast, quiet emptiness in the fabric of cosmic large-scale structure, a place where the universe chose, or was compelled, to be sparse, enormous, calm, and very, very empty. The universe, as a whole, is close to being geometrically flat. This is a statement about the shape of space itself. On the largest scales, space can, in principle, be positively curved, like the surface of a sphere, or negatively curved, like a saddle, or flat, like a sheet of paper, extending infinitely in all directions. Observations of the cosmic microwave background have allowed cosmologists to measure the overall geometry of the universe very precisely, and the answer is, it is very, very close to flat, perhaps exactly flat. This flatness is considered to be one of the remarkable facts about our universe, and it may be explained by a period of extremely rapid expansion. In the earliest moments, a period called cosmic inflation, which would have stretched any initial curvature to near flatness, just as a wrinkled balloon becomes smoother as it expands. The universe, at its largest scales, is quietly, almost perfectly flat. Cosmic inflation is a theory that the universe underwent an extraordinarily rapid period of expansion in the first tiny fraction of a second after the Big Bang, expanding by a factor of at least 10^26 in a period shorter than 10 to the power of -32 seconds. This is difficult to imagine. It is smaller than a heartbeat by an almost incomprehensible margin. But if inflation occurred, it would explain several otherwise puzzling features of the universe: why it appears so geometrically flat, why different regions of the universe that should not have been in contact have very similar properties, and why there are no magnetic monopoles, which many theories predict should exist. Inflation would also have taken the quantum fluctuations of that tiny early universe and stretched them to macroscopic sizes, creating the seeds of all subsequent structure, the entire cosmic web, all 2 trillion galaxies, ultimately traceable to quantum wobbles, blown to cosmic scales. in a tiny fraction of a second. The word galaxy comes from the Greek word Galaxies, meaning milky, which is in turn related to the Greek word for milk. Gala, the Milky Way, was described by ancient Greeks as a faint, milky band of light across the sky. For millennia, humans looked at that band and wondered what it was. Aristotle thought it might be an atmospheric phenomenon. Other ancient cultures had their own stories for it. A river in the sky, a path walked by the dead, a remnant of spilled milk. The idea that it was a vast collection of stars was not confirmed until Galileo turned his early telescope to it in 1610 and resolved the cloudy glow into countless individual points of light. And the idea that the Milky Way was just one of countless similar galaxies was not established until the 1920s. Knowledge unfolds slowly. The universe reveals itself gently to those who take the time to look. Edwin Hubble's measurements in the 1920s showed for the first time that certain fuzzy patches in the sky, called spiral nebulae, were in fact entire galaxies far beyond the Milky Way. He measured the distance to the Andromeda Nebula using a type of pulsating star called a Cepheid variable, whose brightness oscillates in a regular, predictable way that allows astronomers to calculate its true luminosity and therefore its distance. He found that Andromeda was nearly 1 million light-years away, far beyond any conceivable extent of the Milky Way. The universe was suddenly, in a single observation, enormously larger than anyone had imagined. This moment is sometimes called the Great Debate's Resolution, and it is a reminder of how gently and irrevocably the universe expands. Our sense of what is possible, always larger, always older, always more quiet and vast than we knew. The future of the universe, on the longest timescales, is called the heat death, or more gently, the big freeze, as the universe continues to expand, and the last stars eventually go dark, and as black holes slowly evaporate via Hawking radiation. Over unimaginably long timescales, the universe will approach a state of maximum entropy, a state where energy is distributed so uniformly that no further organized work can be done. No more stars, no more galaxies, just a vast, cold, dark, nearly empty expanse of space, slowly cooling toward absolute zero. This is not a sad prospect to sit with. It is simply the direction the universe is heading, over timescales so vast that no human emotion can really attach to them. And right now, we are in the early, warm, vibrant, star-filled, galaxy-rich moments of the universe's history. That is a very good place to be. Many of the heavy elements in the universe, including the gold and jewelry, the platinum and catalytic converters, and the uranium and nuclear power, were formed through a process called rapid neutron capture, or the R process. This process requires an extraordinarily dense, energetic environment where atomic nuclei can rapidly capture neutrons and become heavier elements before they have a chance to decay. Scientists long debated exactly where the R process occurred. Supernovae were one candidate, but the detection in 2017 of gravitational waves and light from two merging neutron stars, a kilonova event, confirmed that neutron star mergers are a major site of R process nucleosynthesis. Two dead stars, the remnants of ancient supernova explosions, colliding after billions of years of slow orbital decay, and in their brief, violent merger, forging the gold that eventually made its way into the world. Gravitational waves, which were first directly detected in 2015 by the LIGO Observatory, are ripples in the fabric of spacetime, caused by accelerating masses. Einstein predicted their existence in 1916 as a consequence of his general theory of relativity, but they were not detected for nearly a century because they are extraordinarily faint by the time they reach Earth. The first detected event was a pair of merging black holes about 1.3 billion light-years away. The ripples it sent through spacetime were detected on Earth as a stretching and squeezing of space by less than 1,000th the diameter of a proton. Detecting something so extraordinarily small is one of the most remarkable experimental achievements in human history. Ripples from a violent event, 1.3 billion light-years away, crossing the universe for 1.3 billion years, and arriving here as a whisper almost too quiet to hear. The universe is full of hydrogen. It is by far the most abundant element. About 75% of all the ordinary matter in the universe, by mass, is hydrogen. About 24% is helium. Everything else, all the other elements on the periodic table, makes up only about 1 to 2%. This reflects the simplicity of the Big Bang nucleosynthesis. When the universe was young and very hot, it could only fuse hydrogen into helium in significant quantities. Everything heavier required the interiors of stars, so the universe began simple, mostly hydrogen and helium, and has been slowly, very slowly, becoming more complex ever since. One stellar generation at a time, one supernova at a time, the universe enriching itself, generation by generation, over 13.8 billion years, slowly building the complexity that eventually allowed for planets, chemistry, and life. The interstellar medium of the Milky Way contains a remarkable variety of molecules, including many organic molecules, molecules containing carbon and hydrogen. Over 200 different molecular species have been detected in interstellar space, including water, ammonia, formaldehyde, ethanol, and complex organic molecules with dozens of atoms. These molecules form on the surfaces of dust grains, or through gas phase reactions in cold, dense molecular clouds. The existence of complex organic chemistry in interstellar space is one of the reasons scientists believe that the building blocks of life are widespread throughout the universe. Amino acids have been found in meteorites. Complex organic molecules have been detected around young stars. The chemistry of life does not seem to require special conditions. It seems to arise naturally, in the cool, dark spaces between the stars. Quietly, given enough time, the number of stars in the observable universe is estimated to be around 10^24. That is, 1 followed by 24 zeros, or roughly a septillion stars. This number is larger than the number of grains of sand on all the beaches and deserts of Earth. It is larger than the number of seconds that have elapsed since the Big Bang. It is simply beyond ordinary comprehension, and each of those stars has its own history, its own age, its own temperature and size. Many are surrounded by their own systems of planets. Many of those planets may have liquid water. Some perhaps may have life. We do not know. But the mathematics of large numbers suggests that, in a universe containing a septillion stars, the occurrence of life and complexity at least somewhere is not extraordinary. It is, in fact, almost to be expected, gently, quietly, across an enormous number of chances. The idea that other galaxies might contain planets, exogalactic planets, is not something we can yet confirm observationally. Our best planet detection methods work over relatively short distances, but there is no physical reason why other galaxies should not contain planets orbiting their stars, just as our own galaxy does. Given that exoplanets are now known to be extraordinarily common, Surveys of the Milky Way suggest that most stars have at least one planet. It is natural to assume that other galaxies do too. There may be more planets in the observable universe than there are stars. More places where the slow chemistry of life could be at work. More quiet worlds, orbiting quietly around quiet stars, in quiet corners of quiet galaxies, spread across the immense, slowly expanding fabric of the universe. We can rest with that image for a moment. Some galaxies appear to have very little or no dark matter. This is surprising, because dark matter is thought to be a fundamental component of all galaxies. In 2018, astronomers reported the discovery of a galaxy called NGC 1052 DF2, a faint diffuse galaxy that appeared to lack significant dark matter. Subsequent observations confirmed this unusual property. How such a galaxy formed without the usual complement of dark matter is still debated. One idea is that it was formed from material tidally stripped from a larger galaxy and did not accumulate its own dark matter halo. Another is that some unusual formation pathway led to a galaxy dominated by normal matter. These puzzling cases are important. They challenge our models and push us to think more carefully about how galaxies form and what they require. The universe, as always, contains surprises. Quiet ones, waiting patiently for us to discover them. The TRAPPIST-1 system, which is only about 40 light-years away in our own galaxy, contains at least 7 rocky planets orbiting a small red dwarf star. 3 or 4 of these planets are in the star's habitable zone, the range of distances where liquid water could exist on the surface. This system has become one of the most studied in all of astronomy. It is a reminder that the universe is not waiting for us. Planetary systems like this have been forming and evolving for billions of years, quietly and slowly, in the dark between the stars. Whether any of the TRAPPIST-1 planets host life, we do not yet know, but they are there, quietly orbiting their dim red star, 40 light-years away. Whether or not we ever look, whether or not we ever know, the universe does not require us to observe it. In order to be beautiful, we end softly where we began, with the vast patient universe, 13.8 billion years old, containing 2 trillion galaxies, each one a slowly spinning collection of billions of stars, each one born from the gentle collapse of gas in the ancient dark, each one carrying within it the memory of the cosmic dark ages, the epoch of reionization, the slow building of complexity across generations of stars. And here we are, on one small planet, around one ordinary star, in one quiet spiral arm of one of those 2 trillion galaxies. And we can think about all of this tonight. We can let these vast and gentle ideas drift through the mind, like clouds across a slow, dark sky. There is nothing to do with these ideas, nothing to remember. They're simply here, large and quiet, surrounding us on all sides, extending in every direction, without end, without hurry, without urgency of any kind. And now, we are coming, very gently, to the end of our journey tonight. We have traveled back, to the very beginning of time, to the quiet darkness, before the first stars. We have watched, slowly and softly, as gravity gathered the first wisps of gas. In the ancient universe, we have seen the first stars ignite, the first galaxies assemble, the grand spirals and quiet ellipticals take shape over billions of years. We have drifted through the interstellar medium, through stellar nurseries, through the vast empty spaces. Between the filaments of the cosmic web, we have felt the slow turning of the Milky Way, the patient burning of ancient stars, and all of this, unfolded slowly, without rush, without urgency, over billions and billions of years. And we can take a moment to notice how quiet it all is, how the universe, in its enormity, is simply here, turning slowly, breathing slowly, aging slowly, just as you are breathing slowly now, just as you are settling, gently, into rest. There is no need to hold on to any of these ideas. Let them drift. Let them float away softly, like slow dust in the light of ancient stars. They will still be here. The universe will still be here. The galaxies will still be quietly turning. In the dark, long after tonight, long after we are gone. Slowly, gently, there is no need to rush. Thank you, very quietly and very softly, for spending this time drifting through the cosmos with me tonight. If these gentle words brought you any peace or rest, I would be very grateful if you left a soft like, and perhaps subscribed, so we can take more quiet journeys like this one together. But that can wait for tomorrow. For now, there is only this, the slow turning of galaxies, the ancient light of distant stars, and the quiet, beautiful darkness. Good night.